All right, so welcome to our second episode of our Tech Amusings podcast. So I have Naveen here, or shall I say, Dr. Naveen. So for those of you who don't know, Naveen, why don't you give everyone your doctorate background?
Yeah, so today it's going to be relevant. So I got a PhD in computer science. It's really the focus was CPU architecture. So I spent time. My goal in life was to go design a chip and get silicon into the field and get it into someone's pocket. So I have a lot of friends who succeeded in that venture. I failed personally, but I spent maybe I don't even know 15 years of my life trying to understand CPUs and the history there. So that's going to be relevant because from what I understand, I think of a lot of what we're going to talk about is stuff that I think is obvious and everyone knows. But I think maybe people don't know some of this stuff. So
Yeah, well, and I think prior to your time working at Pure Storage, which
yeah.
deals with NAND chips, you spent time where?
I was at Intel for 6 years working on disruptive CPU designs.
All right, so Naveen is going to be the expert here in this topic. I'm going to be basically asking Naveen some questions. So, if you think about chips and where they've gone historically, like where have we been at? What has happened in the world of chips to date?
Yeah, so I think it's worth going back and looking at the world that we live in and how it came to be. Because a lot of us, I grew up at the beginning, somewhere in the middle of this journey. But we have lived in this strange world where personal computers, have just gotten better for decades, right? So CPUs have largely ridden, this is now ended, but for a long time, for maybe 50 years, rode a trend called Moore's Law. And what that law is talking about is the density of transistors that you can get onto a single silicon chip doubles every 2 years, or it used to. And for just, I guess, the purpose of the conversation, a transistor it's a semiconductor device that is the basis of computing. It's kind of like a switch. But when we say it's scaling, what was happening is the way you actually manufacture these chips is it's kind of like photography. So there's like a little, and you're going to etch a little transistor onto a die, and as optics got better and we could actually etch better, it's photolithography. So if anyone who understands what lithography is, it's kind of the same concept. You're kind of carving out the design. That would really shrink roughly, I think it was like 30% per generation. And that meant you got more transistors per die, and kind of as a weird side effect, we got performance as a consequence. So everyone correlates performance with Moore's Law. They're not perfectly correlated, but generally it meant that CPUs were doubling in performance as well every 2 years. And that happened for 40 to 50 years. So exponentials have really strange side effects. That means that the computer that I now have under my desk is probably 1 billion times faster than maybe early computers, and that's just like a crazy trend that we've been living through.
Well, one thing we talked about, which I thought was fascinating, is, and I brought this up in our first podcast, was this book about an EMP destroying circuits.
Yep.
And as Moore's laws continued and circuit development happened, how did we make progress in, smaller and smaller etchings and lithography and all of that? And if we reset the clock, hypothetically,
how would we do it?
How would we do it again? Because don't we need the chips to make the chips?
True, yeah. And actually, this is getting a little bit more out of my realm of expertise, but there's even a semiconductor consortium called Semitech that all of the industries kind of pooled together, and that's where they would do advanced lithography research, and they would look several, maybe basically a decade out of manufacturing to say, hey, in order to make this smaller design, we need to be designing 10 years in advance to design the machines, which are computerized, to make those chips. And we need to figure out how the physics is going to work, and we're going to have to solve a bunch of optics problems and material problems. So it was a large sort of communal, almost like joint industry and investment, and this is how we are going to advance the field.
Well, and where I learned about that was reading a book, another book recommendation called Chip Wars, which basically described that history that, we won't cover today.
Yep.
In terms of how that all emerged. But, okay, we're looking at the landscape, right? Moore's law is going on, it's doubling, and it sounds like you're alluding to the fact that it's no longer happening.
Yeah, and I think we can see a lot of this going on. And I do really want people to appreciate what the world is that we've lived in, which is it's for a long time, and I think this has not been true for maybe 10, 15 years, so people are a little bit woken up to this, but for a very long time, every few years you would buy a new computer and it would be way faster, it could do a lot more than it could before, it had double the memory. If you're a gamer, you saw it in the gaming industry, right? So compare, let's say, like Doom from the 80s, or maybe 90s to like a modern computer game now. It's photorealistic. It has like immense landscapes and things like that. Like all of that has happened because we had this free lunch of you could kind of write software the same way, but you could do way more things over time. We saw that end, and I think everyone's familiar with this. That really ended a while ago, maybe in the early 2000s, and we started seeing what we would call the multi-core revolution, right? So prior to that point, everyone would have a single CPU in their computer. Nowadays, if you buy a PC or something like that, it'll talk about how many cores it has. And that just means it has multiple CPUs. And that was a way to continue to extract performance because we could no longer scale each CPU. So we started doubling CPUs, quadrupling. Nowadays, I don't even know, you're probably going to get a dozen CPUs.
But if I look at the size of the CPU, at least, we are using the word CPU in a bunch of different ways. But
yeah.
As I'm building a home computer, the chip looks the same size.
Yes, the die has been roughly the same size. And in that size, it has, in fact, had roughly this doubling of transistors. But inside that die, that die is basically just a piece of silicon. It looks like glass almost. It's going to have now a dozen CPUs inside of it. And nowadays, it'll even have a graphics chip inside of it and maybe some other chips inside of it. So now they've become system on chips is what we'll call it. And that's what's in your phone, too.
Yeah.
And what also happened around that time, which is also relevant to our previous conversation, is GPU growth started to happen. And so what we realized was, hey, there is this form of computation, and this is where I'm not an expert, but this is you can build a chip that has massively parallel kind of compute by design. So these are almost like matrix multiply machines is the way I would think of it. And those have continued to scale, and that's why you see a lot of the AI chips that are continuing to come out, they're continuing to scale. They are massively parallel by nature, and so they are really, one way to think of it is they are putting in more and more compute. And actually, they call them this. I forgot, NVIDIA calls them like compute engines or something like that. They're going to keep adding more thousands of these things per die. So that has all continued, and that meant that the parallel compute world, the graphics world, has really continued to get better. But even that we're starting to see is tailing off like right about now.
Okay, so you're thinking, we got 40, 50 years out of the CPU, and then 10 to 15 out of the GPU, or what's the...
I'm a pessimist. I'm not sure we are getting much more. So the best analogies I can draw are in the consumer's GPU space. So NVIDIA has recently announced their next generation of graphics cards. It used to be the case that their top-end card would be roughly the price of their previous top-end card at double the performance. That's not true anymore. Now it's their top-end card might be, let's say, 50% better, but it's going to cost you about 30% more, right? Mm-hmm. So it's because it's bigger. It also consumes maybe 20% more power. We're seeing that year over year, we're no longer going to get just a better card from these manufacturers because, just physics is starting to fight us.
Well, let me ask you about a different kind of chip because I find this fascinating that, Pure creates a different type of chip called flash.
Yes.
And for a while, we weren't seeing doubling. Like the flash evolution went through a different curve where we're saying, 1 to 2, okay, fine, double, 2 to 5, 5 to 7.5, 8. Like it slowed down, And now, if I took a look at our flash roadmap, 75, 150, 300, we're kind of getting back into a doubling lane. Like, what changed? Why did we go through a slower growth and now a faster growth?
That's a great question. So storage is different. So, or at least it can exploit a different thing. So currently, so the transistor density problem is still true in storage. That hasn't changed. But flash memory has another trick that physics. I mean, the people who are designing these things are like mind-bogglingly smart. Let's just put it that way. So normally when you think of a transistor, you think of it as being on or off, like a 0 or a 1. And in the storage world, in the flash world, you would call that a single level cell. What they've done is basically said within a single cell, we can now store multiple levels of voltage, which is basically saying it's not just it's on, but it's kind of on, it's even more on, or super on. And so that would be 4 different states. And so that was, I think it's MLC, multi-level cell. And then we've gotten into TLC, QLC. We're doubling it each time. There's PLC. And so you're getting doublings from the exact same device by being really careful about how on it is.
Well, and just so we talked about CPUs, and then we talked about kind of matrix multiplication in GPUs. So explain to me why we can't do voltage tricks in CPUs, kind of using, this is
That's
like moving from binary to moving to, a different form of compute that's multi-voltage.
That's beyond my knowledge.
Well, let's project.
But it's mind-boggling.
You're Dr. Naveen. We're
projecting.
Projecting.
Totally. So I would claim that's too complicated. So the simplest way to put it is when we think of compute, we think of it as binary logic. That's really what we mean. And binary logic is it's a different mathematical space. So normally humans think in decimal, right? We count from 1 through 10. Computers count from 0 to 1. That's why it's binary. There's only
why
2.
not make it count to 4?
It's a valid question. There's that the way that semiconductors work. When you have the binary logic system, it's easy to create this concept of there's like these cascading switches. So if I set something to 1, I can maybe turn on the next switch, and if I construct them in such a way, I can make it. We actually use smaller concepts, but you can think of it as we can make it add, right? Or we can make it subtract. And it turns out there's a way to map the entire mathematical space into binary logic in a very straightforward way. And that's what we do. That's how we build circuits. I know of no way to exploit a transistor so that it can do anything other than binary logic.
Well, Flash did that, you just told me.
No, it's a weird trick. So what's really happening, so actually the type of transistor used in Flash is actually a different type of transistor. In the CPU world, you're using CMOS. In the storage space, you're using a floating gate transistor. And you're actually treating it like storage. You are within a cell. Based on how much voltage you're applying, you are kind of capturing a certain amount of charge, and that amount of charge is variable. And then you can later sense how much charge did I get back out. And you can convert it back into the original number. But that doesn't mean I can do math on that. So I can put it in and I can get it back out. But I can't build a cascading set of circuits that can now operate on that, or at least I don't know how.
Okay.
So I don't believe the same concepts apply in the computing.
Do you think someone will be able to bridge that gap? Because look, it's a element. We're now speculating about research, right? The direction, and the reason I bring this up, and we'll get into it, is the world of the way DeepSeek made some of its changes in algorithm, like in its approach to distribution, was actually thinking about basics in floating point math and arithmetic to distribute the problem set in a different way.
Yes.
So I'm just thinking, is a researcher going to come around and be like, hey, you know what we did with Flash?
Do it with storage.
We can do it with compute.
Do it with compute. Yes. Obviously there's super smart people out there, maybe. Yeah. Based on what I understand, I'm a skeptic. Yeah. I think the math becomes Just, I mean, first of all, I don't even know how to build the device. And then if you could build the device, the math might get complicated.
Well, what changes for programmers, right? Because, like, we went from CPU to multi-core. Did the software engineer have to do things differently? What about GPUs? Like, what's the change in the software paradigm?
Very
in each
different.
one of these.
Yeah, so I'd say programmers who lived through this definitely saw it. And actually, we talked about this last time when you and I went to college and were taught about computer engineering. We were taught from the cell level, right? It's like, okay, here's a transistor, and here's how you construct them to build a gate, and here's how you build adders, and so on. That was all because that CPU was a pretty core construct in a computer. If you fast forwarded even to not too long after you and I left college, the multi-core world was already coming. And so programmers or even computer engineers at that time are now taught multi-threading. You have to write a program where there's not just one flow of execution happening, but there's multiple. They're accessing the same memory. You have to worry about data races. They can compete. And so you have to think very differently. The computing paradigm until that point was very logical. Like if this, then that, count this for a certain number of loops. And you can almost follow your program very linearly. And once you started getting to parallel computing, it's like, well, yes, I can think linearly about one thread, but this other thread's going off and doing something else. So I now have to think about almost like you and I working on the same problem together. We're going to split it, and periodically we're going to exchange any piece of information to solve the problem. Like we have to construct that very carefully so we don't stomp on each other.
The good news is, I was helping my daughter with her homework the other day, and it's the standard, like, Joe leaves, his house running 3 miles per hour. An hour later, John leaves his house running 2 miles per hour. They're going to the lake. It's 5 hours away. Like, who gets to,
Yeah.
All of those logic puzzles are built into our education system. People know inherently how to think about parallel processing.
I would argue that that's still linear, though. I'm trying to think of a good analogy of a parallel problem. A parallel problem might be, okay, here's a good one. So if I gave you 10 random numbers and I said, sort them in order, right? Mm-hmm. So if you, with a serial program, you'd probably start moving them. There's lots of quick sort, bubble sort, right? There's a bunch of algorithms that, people might be familiar with, but you're largely going to start kind of swapping. Another constraint is the 10 numbers are in locations and you don't get any other space. Yeah. So you kind of keep moving them, you're swapping. It's almost like Towers of Hanoi.
Yeah.
You keep doing this until they're in order.
Yep.
If I told you now do that, except 2 people are working on it at the exact same time.
Yeah, you split the numbers. These are yours.
So that is one way to do it. So you could basically say, okay, you're going to sort the first 5. I'm going to sort the next 5.
Yeah.
But now we're sorted within our 5. But now we have to sort globally. So now we have to interleave and do a resort, right? Yeah. So already it's more complicated that you and I, by splitting the problem, had to add this merge step that didn't exist before. And that's just sorting 10 numbers, right? So it is more complicated. And then when you get into the AI world, it gets weirder, but I think a lot more tractable. Mm-hmm. So the good news is there's a few types of computation that are what we might call embarrassingly parallel. And I don't know if I should say that AI or large language models are embarrassingly parallel. They're at least extremely parallel. And they leverage a language that NVIDIA actually created. And there's analogs, but CUDA that everyone's heard of is this other programming language that allows you to express kind of the parallelism. And you can think of it as you're no longer thinking in logic like you just described of, there's a train leaving from Illinois to Chicago and it's going this so fast and another, that kind of stuff. You're thinking more in pure math. Mm-hmm. So you're thinking more like, so matrix multiply is an analogy. It's really actually linear algebra. And you're kind of saying I have these matrices of let's say a 10 by 10 matrix, and I kind of want to multiply it, let's say, by another 10 by 10 matrix. And that's kind of how you think, and that's how you program. And by doing it that way, you can actually solve some of the problems that are inherent in how large language models work, right? So that has, and again, this is all history. This has all been done, right? And we've got a lot of efficiency there, and the GPUs, are very good at running these types of programs. And we've lived through this very cool era of technology, right?
So where are we going?
But
Like, what's your thesis?
my concern, I guess, is there's not a lot of juice to squeeze anymore, right? So we've gotten a lot of the efficiency that exists.
But let me push you, because isn't that what everyone's always said about the space? It's like, this is like, I can think of in my lifetime the number of predictions of the end.
That's
you
true.
know?
That's true. But I'll actually challenge you. So I think we are already experiencing some of these things. I think we just maybe don't. Things are still improving. But here, I'll give you a good example. Rewind, let's say 15 years, and I would say that most people who are in the tech industry, every couple of years, you really needed to upgrade your laptop. Mm-hmm. There was just a material need.
Yeah.
Like your computer got slower because the stuff that was running on it was expecting something faster.
Yeah.
Right? And so every couple of years, you would upgrade it. Nowadays, you probably can use your laptop until it fails.
Yeah.
I mean, you're not worried about performance, right? So that's not necessarily a good. I mean, you could argue that, well, like maybe we made the best software that ever exists. It doesn't need to be faster.
Yeah.
But I think actually what's happening is because there's not this doubling of power that occurs, the software is not getting much more power hungry, let's say. And therefore, we can live with the same systems for a long time. There's just not this positive feedback loop of I'm going to give you something that's twice as fast, and therefore someone's going to write software that expects something that's twice as fast. Like that, we're seeing the end of it, right? Yeah. And I think you can see the same thing in your phones. Like your phones can't do a whole lot more than they used to be able to do before, like the new iPhones. I mean, I still get new phones, but I probably skip a few generations, right?
Yeah.
So I think there has been a lot of fear mongering about this, but I think it's also happening.
Yeah.
And I think there's also a lot of curves you can draw in terms of what is the relative performance of compute over time, and these curves are all starting to drop off, right? So all I'm trying to say is that in the world of AI, which is kind of what we started with last time, this is the world that large language models is born into, right? This isn't like the computing industry that we saw from its beginnings, right? This isn't like Doom. Doom was born into a world where computing was growing exponentially and games got super awesome.
Do you think AI is expecting that? Is that like where everyone's at? Like, what's the common wisdom? Is everyone just like, we'll get there?
Yeah. I mean, so let's look at it this way. So let's assume that we live in an AI bubble and we're one of the higher users of these new models, right? Mm-hmm. I mean, I believe, and I think you believe that everyone should be using GPT, right?
Yes.
Or everyone should be using some sort of
AI,
large language model, right? And so it just helps you with everything. Like I use it to edit my docs. I use it to create slides. I use it to, I don't even read. I'll be like, what did this say? Just tell me.
It's like your new Cliff's Notes.
Yeah, exactly, right? Like, but
for those of you who don't know, Cliff's Notes existed for us in the 80s and 90s to give us book summaries.
Oh man, if we live in a world where people don't know what Cliff's Notes is, that is really transformational.
Well, now that ChatGPT exists, is Cliff's Notes out of business?
You don't need it. Yeah, nobody needs to read Moby Dick anymore. Yes. Anyway, there's all these things that you could use, but that's additional compute load on our world. Let's say, right? And where does that go? It's not like computers are sitting around in the world not being used. It needs to go somewhere. So we need to build more compute, which means that's more cost. So someone has to pay for that. And by the way, these things are some of the most power-hungry devices on the planet. Like a modern GPU that can run an AI workload is going to be something like a 400-watt device, 700-watt device. I mean, that's like a microwave. Yeah. Right? And that's just one of them.
Yeah, just for those of you who don't know, your space heater at home is about 1,500 watts.
Yeah, exactly. So, that's how much power it consumes. So if we're saying that, okay, we're at this point where we've just transformed the world with a new technology, and now, let's say, a few % of us are using it, or maybe it's being used to a fraction of a percent of what it could be used for, where do those orders of magnitude of additional use get put?
So what 6-something billion people on the planet? Is that kind of the thing?
Exactly, right?
So we're probably saying, I don't know, a few 100 million are using AI today, maybe.
Maybe. Yeah, and
right.
then, and even the people, even when you and I are using it, we're using it maybe not as much as we're going to. You and I are probably going to ramp up our use by an order of magnitude.
Yeah.
I want to.
So there will be a generation of people, like we said in our last podcast, who are born in the AI generation, and it will be part of their lives, right?
Exactly.
We're not that generation. We're born pre-iPhone even.
Totally.
So let's say it projects out. Like in any time anything's scaled this way, there's always been like growth, innovation curves, and efficiency curves where people are like, okay, now we need to focus on efficiency and cost and all of that. So we're like, you mentioned the juice, right? There's a juice and a squeeze.
Right.
We haven't yet tried squeezing the efficiency out of this. Where do you see the efficiency game going?
Well, I guess my long rant was to try and argue that at least some of the places that efficiency squeeze could happen has already happened because it's just a silicon device, right? So that a lot of the spaces where we could squeeze efficiency, like we've already done that. So there's no more there, or it's diminishing. But I think we just saw there's a recent paper from DeepSeek where they released a model that was as competitive as larger models from like ChatGPT or Google or Meta, and it used an order of magnitude fewer parameters, so that you could think of it as it's a much smaller model. Therefore, it used an order of magnitude less compute, a lot cheaper. And if you go and dig into it, a lot of it's from algorithmic changes that they made. So they, and I'm definitely not an expert here, but they looked at the way that you train these models, and they found some efficiency that they could get from how you train them. Like one of the ones that they mentioned is they used lower precision floating point, right? So they used 8-bit floating point versus, I don't know if modern models use like 32-bit floating point, or let's say they use 64-bit floating point typically. That means you can do 8 times as many calculations with 8-bit than you can do with 64-bit. You lose a lot of precision, so it's kind of, you lose some information, but they somehow have found a way to deal with that. And that's a great algorithmic change, right? That's an order 8x, that's an order of magnitude roughly, right? That they got out of just that tweak. I think that the algorithms in the LLM world are new enough that we'll probably see a decent amount of that, right? We'll see some algorithmic improvements, maybe a few more orders of magnitude. But that's the problem with exponentials. Like that, you just can't assume that's going to keep happening. You're going to start getting diminishing
there's multiple
return.
areas of where you can focus on efficiency,
Sure.
right? So algorithmic's one for sure, but like let's think about the cloud, right? When one area, I think you've mentioned this to me in the past, was when the clouds came about, the efficiency happened differently.
Yeah.
How did that efficiency happen?
Yeah, so I think maybe just data centers in general, or maybe the move to the cloud, that also gave an efficiency curve that we as a society rode, right? And what was happening is, and this happened both in on-prem data centers and really in cloud data centers. It's kind of the same concept. That by consolidating workloads through virtualization, we could run, you no longer needed to have a separate box and its job was to run a database, and another box whose its job was to run your support software or so on. Neither one of those things could fully utilize that. And when I say box, I mean like literally PC, computer. You can never utilize the resources in there. So what we can do through virtualization is pretend you have multiple virtual PCs running in the same machine. And by sharing the resources, you can now run twice as efficient. You have twice as, you're taking advantage that your compute is idle. It's not being used all the time. Its memory is not being used. Just start cramming more workloads into the same thing. That's kind of what the cloud did. We rode that curve for a while, and now we have, if you look at Kubernetes or containers, like we've gotten pretty efficient at utilization.
Well, so, that it's interesting because, if I think about some of the first timeshare systems started with tandem computing and mainframes, right? It was just like, okay, how many MIPS are you going to do? And everyone's timesharing a job.
That's right.
Right. And,
it's kind of the same concept.
Every company had their own, mainframe at one point, and every company had their own data center, and the cloud gets some benefits of scale by running multiple things in a timeshare, basically.
Yep. Very similar.
So do you see time sharing as something like, is that efficiency baked into AI scale model, or is there a new way of timeshare, right?
I feel like it must already be there.
Yeah.
Right. I think that ChatGPT, for example, as a company, was born in that world.
Mm-hmm.
So I'm assuming that when we all go to the ChatGPT app and type something in, we're really all using the same compute in the background, and it's being load balanced amongst us. So maybe I have to wait until some compute frees up, and then my query can go in, or my chat can be serviced. So I think that efficiency. I'd be shocked if there's a lot of time sharing efficiency left in the tank. But I could be wrong. I don't know exactly what these people are doing, but at the very least, that's a low hanging fruit, and that'll go away quickly.
Okay, so let's play this out. So you're saying we're gonna have there's not a lot of places to squeeze the efficiency. Algorithms you think aren't gonna scale like algorithmic efficiency.
We're not going to get 1 billion times better through algorithmic efficiency, right? Because remember, that's the analog. I think the thing we lived through in the PC world was, memory went from a kilobyte to, let's say, you can have a terabyte of memory in a computer now. That's 1 billion times more, right? Are we going to see that? Not from algorithmic.
Yeah.
Right. So yeah, sorry.
Yeah. So okay. So we have an efficiency problem then. We're not, and we all think when we're looking at AI that AI will at some point in the future be able to reason. We picture Asimov, we picture things, and I kind of refer to sci-fi books, but if we go out into the future, what are the things holding us back? Because if we don't have efficiency, what are we going to run out? If this was a lifeboat exercise, what do we run out of first?
Yeah.
Right? Is it computers? Is it power? Is it space? Is it thermal? What do we run out of?
I think the one that's kind of a hot topic these days right now is power. I think that's a pretty obvious one, especially with our concerns about getting more efficient with power usage and having more renewable energy and so on. Data center power growth. I think data center power we were trying to was kind of coming into control, I would say, for a while, and I think the AI boom is going to send us on a totally different curve than we had anticipated. So I think people are going to stamp out more data centers to solve the problem. So that means you need. These data centers are large. They look like warehouses. So you're going to have to go find physical space that's going to consume power that is, if I'm not wrong, it's like on the order of a gigawatt that you need to run a data center. That's a power plant. Yeah. And so now you need a new power plant.
It was interesting, right? Because you were talking about the squeeze. One of the things that, I've got firsthand experience on is we at Pure recently did a deal with a hyperscaler, and the whole basis of that was for them to bend the curve on power associated with data growth, like watts per terabyte, right? And it's because, as we're building more dense drives, we're able to consume exponentially less power as we get, we're still 2x scaling factors every year right now for a while on NAND.
Yep. NAND
so that's a place where we're squeezing, right? We're able to squeeze the power envelope. And like you're saying, you project out at some point the juice, worth the squeeze will probably change, right? But we're probably in, maybe have another decade of that. Who knows?
Yep.
So power is the limiter. That's what's going to prevent everyone using from AI. And humans always solve for the thing that's holding them back, right? That's where the research, that's where the innovation, that's where the dollars go.
Yep.
So how do you project that playing out? What do we need to do to ensure AI continues to grow?
Yep.
And, we don't run out of power.
Yep. And I think, and by the way, just to come back a little bit on the storage thing, storage is interesting because storage is still on the efficiency curve. So if you look at what people typically store, a lot of storage out there is still on spinning media, so disks, and those are inherently more power consuming than flash because at rest, flash doesn't really consume much power at all. So just moving to flash will provide some power efficiency gains, and then you start to get into dense flash, and so there's more efficiency gains. So the horizon for storage might be a lot better. But I just want to clarify the LLM world, yes, it needs storage to ingest and train on and so on. But to actually perform its training and then even the inference, us using it, it needs a lot of GPU compute, and that, yeah, that's not. I'm claiming there's not much efficiency left there. And so, yeah, coming back to your question of how do we solve this, I don't know. I mean, I'm hoping for like some. I've seen some reference of the hyperscalers looking at small scale nuclear. So nuclear. I mean, we're getting back into conversations that we've had as a society maybe 10 years ago, 15 years ago about where does our power come from, right? And I think we've seen some really nice trends in terms of, hey, we can use wind power, and solar's been doing great, and conversion from coal to natural gas. These are all great trends. And then out of nowhere comes this massive demand for additional power. And now people are saying like, oh crap, this isn't about replacing the current grid with existing demand. It's also solving for massive new demand. And conversations that I thought as a society were tabled like, nuclear, we don't really like that much. Like they're all back, right? We're talking about extending the life of nuclear power plants. We're talking about small scale nuclear reactors. If anyone follows like energy research, like fusion is always on the horizon. Like if we get fusion, like that would be awesome. So that's a free lunch.
I think I'm going to claim that. I'm going to go out there and just state that I think to get AI, I know Meta makes all of these, and OpenAI, Sam Altman makes all these predictions, but my prediction is we will have to solve an exponential step in energy with something like fusion to get AI to the point of reasoning.
Yeah.
Right. I like I'm saying, I think there are limiting factors of that magnitude.
Yeah, I think if we wanted to get to true reasoning intelligence, first of all, let's assume that can be achieved. And I think we're also both assuming that you need quite a bit more than what you could do with current LLMs, right?
Yeah.
And so, yeah, I think that if that's where we want to get to, then yes, I think fusion is what gets us to the next step function. So without that, I think we're on like we talked about efficiency curves, but I think we might also be on a LLMs are kind of tapering off in terms of what they can do curve. Like maybe we're not there yet.
Yeah.
But in a few years, we might see that. It's like, okay, these things are cool and they're awesome and everyone should do, and they're transformational, but are they going to go much further? I don't know. Without algorithmic change or massive different ways of building a neural net or something like that, the actual hardware itself isn't going to give us that, and I don't think we're going to be able to build enough data centers to give us way larger models and so on. So.
Well, let's think about some of the policies. So I think I shared something with you I read in the press that said, hey, some large-scale data center providers are actually looking at directly hooking into a power plant.
Yeah.
Right? So we don't need a grid. Let's just build the data center next to the power plant and just pipe transmission away so they're not having to deal with the grid, right?
Yep.
And what's fascinating is the policy changes because our electrical system was built on this idea of you subsidize the grid use. Because power is an interesting thing that I think people have to understand. In the industry, you can produce it, but you can't store it necessarily because
I actually didn't know that.
If it's not used, it dissipates.
Oh, I see what you're saying.
So, and yes, you can. When batteries came around, lithium ion and different battery technologies in power, they smoothed the curves between peak and peak load and production. Right. So you could eliminate wastage because I think some of us are familiar with the power company giving you an incentive saying time of use, don't use it at this time. It's all to smooth peaks.
Right.
Because you send it into the grid, and if it doesn't get consumed, it dissipates.
Yep.
Right? So we will probably need to think about one, production. Two, we probably need an exponential step function in batteries, right? In terms of what we could store. Time sharing will help kind of eliminate idle versus peak, right?
Sure.
So I think that's true in the curve. But then what about transmission, right? Do we think we're going to end up with okay, let's just in the future dedicate maybe the island of I don't know, New Zealand is the world's power plant and data.
No
all
offense
eggs
to
in
anybody
data.
from New Zealand.
Yeah, we're not looking to wipe out any sheep or anything, right? But like the nature of, choosing a thing, with density and with aggregation, you get efficiencies in design, right? When you're trying to solve this stepwise function of like, we need power, we need batteries. And, one of the battery researchers, I read this a number of years ago, the guy who invented the lithium ion battery, I think Texas A&M professor, right, was in his 90s. I don't know if he's still alive right now, but, he invented lithium ion, and he invented a new salt battery that's like 100x more than lithium ion in terms of power storage and density, and that based on like salt versus lithium ion, right? So it's interesting. It's like the guy who invented it, it's like was the same guy disrupting
That's pretty
his
cool.
own previous work. But there were papers around fusion. There are papers around this next battery thing.
Right.
I don't know that there's been a fundamental change in grid transportation, of energy, all of that.
Yeah.
Is like, we haven't thought through that. Like, I know in Ethernet, and this, like,
Yep.
we've had to think about, 1G, 10G, 100G, like stepwise functions in bandwidth across the wire. I don't understand where the research is at in terms of, do we need to rerun transmission lines? Are we like going to be stuck in bottlenecks anywhere in the chain?
That I don't know. I mean, I do suspect that's why some of the hyperscalers are interested in just hook me up to the power plant directly, please. Then you bypass that problem to some extent. But yeah, I don't know. I think my mind goes in a different direction, though, which is, even if we can solve all of these problems, nothing we've talked about sounds cheap.
Mm-hmm.
Like, so... well,
explain cheap, right? Like, how expensive is this stuff today? Like, how much are people spending on data centers?
Yeah, it's a good question, actually. I don't know the recent data center spend. I know that building out, let's say, a new fabrication facility for chips is going to be somewhere around $10 to $20 billion, right? Okay. Now, building out a new data center, I'm guessing, is on the order of billions plus, like 10 billion. I'm guessing is not out of the realm of possibility. So these are not cheap. You need many of them. We're going to need many more of them. We probably need to refresh the hardware inside of them. So yeah, I mean, I guess I haven't done the math on what the global cost is, but
or e-waste.
So yeah, that's true. So if LLMs do take off like they are taking off, I mean, people are going to gut their existing data centers and put in a whole lot more GPUs and so on. Like, yeah, we are going to refresh our entire compute world. By the way, there's another option here, which I think the industry is already following, and that'll also lead to e-waste. That's what made me think of it. Is we talked about how that the PCs that we haven't need to be refreshed for a while, right? You had a laptop, you're fine with it. Well, now everyone is starting to put in, they might call it like a neural engine or some sort of AI chip inside of their computers, or it's on your phone, it's on your laptop, Apple Intelligence, right? It only runs on newer iPhones because there's a neural processing unit in there. I think that's what Apple calls it. Well, what is that? Well, it's that same type of compute that we've talking about, this like massively parallel, almost like graphics like compute, now running just in your pocket and your laptop. I do think the industry is rotating towards saying, well, we may not be able to build enough data centers to satisfy the growing use we anticipate, so I'm just going to put it in all your stuff. So it's going to be everywhere. Now, every chip that ever gets manufactured everywhere is going to have some sort of AI engine in it that can do local reasoning.
So then we're all just paying for the power versus our provider paying for the power.
Exactly. So just let's invert the problem. Let's just replace the thing that everyone has. You already somehow power it. You somehow already have it, and you're going to, you want to refresh it. And so we'll just put the power in your pocket.
Well, it seems like the industry's cyclical, because previously it was like, let's centralize everything into the cloud. Now let's, put it back in where, in a distributed thing. Yeah. And, if I think I see it going maybe in a slightly different direction, right? Because I think, yes, I see that happening, but I think of like the pattern is always interesting of centralized versus decentralized. And I think what I project happening in the future, and DeepSeek, started looking at some of this, was distributing problem sets and persisting elements of that distribution chain, right? So go with me here because this is a little bit sci-fi-ish, right?
Okay.
In compute, we talked about stateless and stateful in containers kind of land.
Yep.
Right? So if you apply chain of thought in AI algorithms and you persist state, like compute state in a chain of thought, right? Because that's how they're getting larger and larger context windows.
Yep.
Could you, in a timeshare world, cross a context window where you persist common linkages in a chain of thought?
Yeah.
And if you persist those things, you no longer need to compute. Don't know that a different way of thinking about algorithmic efficiency is no longer needing to reprocess
Yep.
common queries on a shared time space model.
Totally. So that's I think in computer science we'd call that memoization, right? So it's like you just remember that you did it before and kind of reference it again.
Yeah.
I think you totally could do that.
Do you think it'll work, or you think that's a kind of nonsensical?
I think it's a reasonable approach. I think where people will get concerned, so there's a tension there though, which is I think we're worried about privacy and information leaking. So if you and I are sharing a model and I'm asking it about help me with my tax return, and I'm trying to not go to jail. I don't do this, by the way. but pay as little in my taxes as I can, right? Can you help me do this, right? And then you come along and somehow the system decides that we should share the chain of thought or share the model. Like suddenly you maybe got access to my financial data, right? And you could start at oh, weird. But
aren't we already seeing some of that in ChatGPT land today?
True. Yeah. And that, yeah. So
you can ask Jill, not deviant thought, right? Not topical to this podcast, but there's a lot of papers around how to reverse engineer, ask questions to understand training data.
Because of some of the reinforcement learning that's going on, some of what you're communicating into it is kind of getting back into the model. But yeah, at least for enterprises, and I thought if you paid for ChatGPT, so if you use ChatGPT Pro, they don't guarantee that. I don't know. I thought there was maybe a way for me to pay for a model where that doesn't happen, but
look, at an enterprise level, companies do it, but you're in your own isolated space within your company domain, right?
That's true.
Not within your individual domain.
That's fair. Yeah.
Right. So I think.
Yeah, that's fair. So maybe that's intrinsic, and they'll just be like, it could happen anyway, so just do it.
Well, look, we're trading off different things,
Yep.
right? I think you brought the perfect example earlier when we were talking about solar and wind and whatever. We were trading off clean energy, and now it's necessity is the mother of all inventions, and we're talking about nuclear energy, right? So when you hit bottlenecks, what are your trade-offs?
Yep.
And I think, is privacy eventually a trade-off towards algorithmic shared efficiency in a chain of thought model?
Could be. So but I'd like to go a different direction, which is let's say we project out and it is a zero-sum game. And to some extent, we need to just start paying for it. There's a limit to how much we can build per year. These models are already expensive. It's unclear if they are providing return on investment for the people running them.
They are not yet. It is clear they are not yet.
So, based on your, and this is totally just spitballing, right? But I find this thing incredibly useful. I'm still cheap, and I don't really want to pay a whole lot for it.
Yeah,
right? But
you and I are similar.
So I can imagine that most of the world is like this. If we do get to this zero-sum game world, what does that mean? Does that mean that the financial model means that, okay, it doesn't matter what it can do. If we can't make it pay for itself, we as a society are just not going to do it, right?
Well, and I think, there's a lot of, if you listen to all the, big five model creator tech CEOs, they're the cost of not investing is larger than the cost of investing. So burn the bridges.
Yeah.
I'm going to do, dump X billion / trillion.
The income will come.
It will come, right? And that's people claimed that in the past.
Totally, and it's played out.
Sometimes.
Sometimes, yeah.
Sometimes it played out. Sometimes it didn't play out. I do. I'll give you the personal anecdote. Generally, I was a big use pre-ransomware of download software off the internet that was free and try it.
Right.
right? Since ransomware, and I know what's out there, I don't like. I was just like, public service announcement: don't download any software off the internet, right? Exactly. Everything's polluted and it's terrible.
Totally.
But like, you can download off GitHub and compile your own repos, right? Like, but basically, I lived off freemium software, and whenever there was a utility where they're like, the vendor's like, pay for it, I'm like, I'll find another freemium utility.
Exactly.
You know what I mean?
Yeah.
So I was fairly, for most of my life, unwilling to buy software. And, that's interesting, right?
Right.
Quicken is an example of something I did buy into early on and stuck with. But I wasn't a prolific buyer of multiple software packages.
Yep.
Right? And then in this AI thing, like, there's a lot of freemium things, and then you run out of tokens, and you try it, and that type of thing. And I've gone down that route, but I've actually, put some money into a few, because I was like, the return on... But I think it wears out after a novelty period. Right?
Yeah,
There's I learned this thing, I know its pros and cons, I know what it can do for me, and are there freemium alternatives?
Yep.
Right? So I think, there... And I'm not saying everyone's like that, right? We're in high tech, we'll go compile something ourselves if we need to versus, pay for the consumer version.
That's right.
Right? But I have a hard time thinking that the amount of investment will lead to a return on investment for those people making the investment, right?
Yeah.
I think society will benefit.
Exactly.
Right? As a whole. Do I think they'll be able to get consumers to foot the bill? I think Apple has kind of figured out how to charge $1,000 per phone.
Fair.
Right?
That's fair.
How is, will ad suppliers charge it, be able to, at some point, at that's how Facebook happened, right?
I didn't think about that.
You got ad and bias, to monetize is, could you sell bias to pay for it? Do we have to?
Oh, man. That made me really depressed, because I think that may be a real revenue stream, right?
But
I'm putting a lot of information.
Google makes ad money. Facebook makes money. Their primary monetization vehicle is advertisement.
Totally.
There's a reason why you're willing to I need X number of consumers on my platform.
Yep.
Right. So you can monetize eyeballs.
Yep.
So how else?
Yeah, I mean, that one's a good one, because we already joke. I think everyone jokes about that Alexa's listening to me, and when you're talking about your kids' swimming lessons or something like that, all of a sudden you get advertised swim goggles or some stuff like that, right? So whether or not that actually happens,
I'm
clear.
Convinced.
Exactly.
So I know I'm going to go check my phone, and swim goggles are going to be there.
Totally. And so now if you start talking about these large language models, I know me personally, I'm putting all sorts of junk in there. If they can associate that back to me, they might predict things that I actually want, which I actually try not. I might buy it because I'll be like, wow, I actually do want that.
Do you use AI for research, to buy things?
So I want to. I haven't successfully pulled that off, but that's another thing that could be useful. So I'll give you an example. I haven't tried this again recently, but I had a very specific use case where I have a garage and I wanted to hang 4 bicycles in it. And I wanted them to be next to each other, but I wanted it to be staggered. And I'll try this again, but maybe you could try this for yourself. Go to Amazon and start looking up bike hanging gear.
Yeah.
And you'll find out that there's 5,000 options. And what you're trying to do is not easily translatable into the things that you're being offered. You'll be like, well, this one is 12 inches long and has
look, we all used to think about how to ask the right search question.
Exactly.
It's 5 staggered. You're trying to add them into your search query.
Exactly.
Right?
But now I want to be like, look, this is what I want to do. I want gear that works. I want it to last. I want it to be, and I would love to have that shopping experience.
Well, so let me ask you this, because Amazon I think they call it Rufus or something. They have
I haven't tried it.
AI thing, right? Where you can do the prompt engineering, ask, or you can still search using ChatGPT versus Rufus about Amazon and other things. Do you believe vendor-specific models are going to be superior to non-vendor-specific models? Or how do you see
I think that it will. Like, I mean, I think that if, you know, Amazon, for example, tailors to their own storefront and how it works and how they get comments and so on. Like, I think it'll, you know, I think they could give us a materially better shopping experience. So yeah, no, I do think that's.
But what about the human behavior side of it? Because part of me is like, I always think about like the sponsored side and like the things that show up first. I'm like, usually the cheapest one isn't the first one that shows up, right? Like there's a
That's fair.
like vendor bias.
Yeah.
In the model.
So actually, there's a monetary driving incentive for the vendors to have their own models. That's for sure. Like always, make sure Amazon Basics always shows up at the top, right? And sponsored shows up below that, and so on. Yeah, absolutely. So I actually think that could lead to some support for this. I don't know about you, but
I'm going to try to link our two conversations about shopping and power together. Right?
Okay.
So here it goes. This might be a failed experiment. The industries always try to come up with metrics. Advertising has certain metrics, right? Like if you think about ad revenue, it's like, okay, what's your ad funnel? What's your search volume? What's your, conversion rate? Like there's certain metrics that kind of exist in advertising. And when there was a period of time, concerted effort around, like, I remember late 80s, early 90s about, like, there's too much spam in the mail, we're killing too many trees. So how do you, like, opt out of junk mail?
Right.
There was, like, a concerted effort to, like, allow that. There's even congressional things that say I have the right to not get emails if I, like, every email, like, in a marketing thing has to have an unsubscribe button, right?
Right.
So if AI is used, and it is this exceedingly large power draw, and it's in the hands of advertising and consumerization, right? Like you're basically going to spend like a larger and larger portion of the power envelope over time for what I would consider spam.
That's true.
Right? There could emerge a, watt per advertisement type metric.
Right.
Right? And, I think that efficiency, right, could become a non-technical problem, but a policy problem.
It's like you must be able to turn this off, or
Look, it started in like mail and paper and trees.
true.
I'm trying to just projecting that into tech, right?
Yeah.
Will there be an intersection of like policies?
It could
right?
be. And I think there's a corollary actually, which is I don't know if you've been following. What are these called? I think they're called. People are calling them tar pits, I think. So there's a growing group of people who really don't want their site crawled because they're essentially gets ingested into the AI model and it becomes part of the LLM. And so what they've done is started to create these malware where when the crawler comes in, it effectively traps it and starts feeding it garbage data to try and pollute the model.
Oh God!
So this is kind of an emerging trend, and so that's terrible in a couple ways.
And now I got to research this.
One is that first of all, like if we talk about power, like we're wasting a bunch of compute on nonsense because this person just trapped at the crawler, and then the second thing is the reason why it is all happening is because someone wanted to opt out. They're like, I don't want this in these training models. And so I could see also legislation there around, hey, I should be able to enforce you cannot ingest my data. And if I have logs of you came in and you crawled my data, even though I have a file that says you shouldn't. Because by the way, I think there already is a convention around this.
Well, like we were talking about, like, could artists do that with AI, right?
Yeah,
like,
exactly.
So even since, we talked about our first podcast and I mentioned Suno, they're in lawsuits by artists about
really?
being training their voices, right?
Right. So I think that some of these things might be related. Where it's like, okay, I want to I want to opt out of all of this, and that does, I think, result in efficiency gains. But I actually was going to ask a different question, which is, let's assume that advertising, yes, I think I concede that like money is going to definitely come from the advertising world. It always does. This is everything I ask is going to somehow come back at me in terms of something I'm going to buy. Totally true. I think that will absolutely happen. I think we're also going to see GDP growth because of these tools, right? Like each of us can produce more. I think that's
You're on
true.
the positive side of humanity. I'm going to take on the over-under, I'm going to take the negative side.
Really?
100%. So,
Why?
Um,
I didn't expect you to say that.
this is a difference between a technologist and a behavioralist, right? So I and we've done some research on this in storage, right? Like data needs to grow,
Right.
but based on GDP budgets being fixed, people will find what data to delete to fit in their budgets versus do more.
Yeah.
Like so the question is what defines need, and money also defines need, right? So while you see a small cohort of the ultra wealthy, like top 5 companies over investing in a segment, not everyone has the unlimited capital to overinvest in a segment.
Makes sense.
So when you take a look at behavioral principles and organizational and GDP and capitalist principles, like I do believe that there will be a split cohort. There will be the efficient cohort that cares about efficiency that will get ultra efficient. There will be the growth cohort that cares about growth and will use this to grow faster. Right? I think those things will exist.
Okay.
But I believe that's a minority of the human population. Like, I think most folks are in the middle, and they'll be like, oh, I used it to check my grocery shopping list. You know what I mean? It's not going to be used for...
It's marginal.
It's marginal. It's not used like... And I think from a law of large numbers and, social scientist standpoint, I would argue that the production comes from a few, not the many. Right? So that, that's always how economics has worked in the past. Like there's the few creators. There's a second tier of people that ride the coattail of creators, right? And grow and do that. But that's still a minority of the population.
Interesting. Okay. So what I was going to go with that was like, okay, if everyone gets more productive, then somehow there's money there, right? That could pay for this, but...
and it's funny, we can get into a philosophical debate of what's money, right? Because since the gold standard was devalued, the only value of the dollar bill is what we think the value of the dollar bill is, right? It's not like money has no intrinsic value other than belief in that money.
Sure, that's
right. And like money's a belief system, right? And so it is fascinating that it goes there. But I'm going to come back to that efficiency thing for a second, right? Because let's play a non-ad use case.
Okay.
Right? We all know robocalls. And you're an engineer. Could let's say AI gets used with more text message or robocalls or whatever.
Yep.
Could you just have your AI be like, when I get this text message, respond this way, and eventually the robots are talking to the robots, the compute bill is churning,
yep.
Right? And the AI middleware of instead of human to human, it's machine to machine.
Yeah, I
right?
think that's going to happen for sure. That's my belief, right? It's almost like the equivalent of I'll have my people talk to your people.
Yeah.
Except now
my people are way.
And so it's like, hey, Prakash, I want to meet you for lunch sometime, and you'll be like, let me check my calendar. And be like, man, I don't want to do any of that. Just if a lunch request or scheduling request comes in, let my LLM try and offer something back. And then your LLM can offer back a negotiation, and it'll arrive at something, and maybe both of us have to approve it.
So do you think admins are screwed then?
I think hopefully they get to do things that are not as annoying as scheduling calendars.
Very well, but
I mean that's a whole other topic, which maybe we can come back to
another day.
Which is
what is the human element here?
What happens to jobs, right? I mean, there's an interesting aspect there. But yeah, coming back to the agent, do I have my own agent, personal assistant kind of thing?
Yeah. I would project that. I would say my kids, right? Maybe not my kids, but my grandchildren will have an AI personal assistant be part of their life. That'll be a thing. Whether it's on a phone, whether it's a virtual avatar, whether it's the pop-up hologram from Star Wars, who knows? But
I think it'll be my kids. I don't.
You think your kids?
I think it's.
I think things take longer. They just
maybe
do.
They could be. It could be the equivalent of Clippy. Right, that might be what they get, but I think that's going to happen, right? I think they're going to have
Clippy already happened.
For anyone who doesn't remember that, Was that Microsoft Word? Yeah,
Yeah,
it was
it was
Microsoft
Word.
Word. There would be a little paper clip that bounced in your document and would try and offer you totally useless help, like, "Hey, did you know you could save your document?" And be like,
At
yes.
least they tried a co-pilot. You know what I mean? Maybe before their time, maybe before compute was ready. But, like, at least they tried.
They did try. But no, I do think that kind of thing is going to come back and hopefully be more useful, but maybe not what we're talking about, like a actually fully functional, assistant. But,
All right. So if we're trying to summarize, right, like this podcast, what do you want people to walk away from this podcast in summary with? Like, what is your public service announcement?
I think maybe in some sense it's to put a little bit of pessimism into the whole AI scale discussion, right? I think there's this belief that AI scale is exponential.
Mm-hmm.
I think that's kind of what really people have in their heads.
Yeah.
And I think I'm trying to claim like it can't be exponential.
Yeah, I think we don't have, any disagreements on that. I do think, though, necessity is the mother of all invention, right?
Right, yeah.
So I do believe we can't see it yet. We're
That's
pretty bad at predicting the future. But I do see, not Moore's Law, but stepwise changes
100%.
in the efficiency curves in different ways.
Yep.
Don't know what all those ways are. Will give us a runway well beyond our lifetime and maybe our kids' lifetime. Like, I do think there's a lot of room.
I think we've got, and that's where you and I differ. I think the next 5 years will be massive in growth, and then I think it'll kind of peter off. Unless something dramatic happens, like we just discover new materials or fusion.
But I'm saying
you're banking on
because we're talking about it right now, right? And it's in the common.
Interesting.
Because we're talking about it and we've identified the problem.
Yeah.
Research and dollars will go into it.
That's right.
Thought will go into it, and someone will crack it.
That's fair. Yeah.
Right? It's not going to be me, but someone will crack it.
What is that in sci-fi? There's like you can measure like the level of a spacefaring species by how much power it consumes.
Yeah.
And so like fusion's one. Then eventually you could build like a Dyson sphere and consume the power of a sun. Then you consume multiple suns. Like
what was that? That was in Foundation, right?
I think but there's I'll have to remember it. Maybe we can link to that. But I mean that's very possible.
Yeah.
So.
All right. Well, thank you everybody for listening today. That's a wrap.
Yeah. Thank you very much.